As you see, the title of this session is called Accelerating Beyond 2 Nanometer Chip Innovation Across Europe. This is the core of the activity of the NanoIC Pilot Line. Today, this pilot line is already active since almost a bit more than a couple of years. And it focuses on, as the name says, on 2 nanometer leading edge system on chip systems. It has main interest in 3 pillars: advanced logic, novel memories, and advanced interconnect technologies. We cover these 3 pillars with 4 main actions. We are preparing our pilot line already in our 300 millimeter fab, and the upcoming new fab, which is soon to be constructed, an extension of all the infrastructure and equipment in order to support our modules and fabrication flow for this technology, which, as you can imagine, are still under development and quite complex, as our colleague later will explain in detail. There is an enormous amount of technology development ongoing here in the pilot line. We are literally discovering the next steps of what semiconductor industry will look like in the next 5 to 10 years. Today, we are interpreting that following the NanoIC, if you want, also Imec, of course, philosophy, but of course, there is much more than that. All these beautiful things would be not really important if we could not give access to the European semiconductor community. And that's why there's a strong component of access and selection process that we have in the pilot line. We deeply care about it. We have great attention on all the sensitivity of the data that we share with our customers, with our users. That will also be covered during the presentation. Finally, and by far not because it's not important, education and workforce development play an incredible role in actually, they should play even a more important role today in the European ecosystem. Why? Because we lack a lot of good engineers that in the future will have to continue and exponentially grow the technological development that we all need in all different fields, not only, of course, the NanoIC one, but all the ones that are covered by the other pilot lines, which brings me actually to the next slide, but not before I say that the pilot line, as well as all the NanoIC one, but as well as the other pilot lines, it's done by a consortium of entities. It's Imec, Sialetti, Fraunhofer, Tyndall, VTT, and CSSMT. Today, we do envision the pilot line. This is the CHIPS Act Pillar 1. And this is how we do envision the position of the pilot line within the CHIPS JU. Together with the design platform, they represent a little bit the engine of the CHIPS JU. And here today, we can already say we have 5 pilot lines active. I will go through that in a moment. Upcoming, and some of them already started, quantum pilot lines. And of course, how do we reach them? How do we reach the design platform and the pilot lines? Well, there are different ways. You can directly contact the pilot lines, but also, and that's where the SCCC plays a pivotal role and will play even more in the future. I'm pretty sure the role of the competence centers will be fundamental because they are the only entity that are capable to understand what's going on each and different country in Europe. We are 400 million plus individuals here, and we with very different backgrounds, and in Europe we all need guidance, and the competence centers are the perfect place to guide us and all users towards the different pilot line services. As I said, we have 5 pilot lines at the moment. The NanoIC one, focusing on beyond 2 nanometer system on chips. Then we have FAMES pilot line, focusing on FD-SOI technology, led by Sialetti. APEX on heterogeneous integration and packaging, led by Fraunhofer. We have the PIX Europe, focused on photonics, led by ICFO. And then the wide bandgap material, WBG, led by CNR in Italy. All these initiatives cover, as you can see, a very broad spectrum of technologies, but this is fundamental. This is not a war, if you want, that we can play in this case only by looking at a single aspect of the technology. No, we have to look at it from an holistic point of view, and that's what we are doing in CHIPS EU and in the pilot lines. As I just said, we have several partners in our consortium. Imec is the project coordinator. We will focus, of course, on the three main pillars, but of course, in the other institutes, like, for example, Tyndall, there are beautiful initiatives and technology being developed, being 2D materials and other deposited semiconductors for DRAM application. In CLET, we work a lot on next generation CFET architecture or 2D materials for DRAM. VTT is focused on high frequency characterization, all the devices that we fabricate. Fraunhofer will work on IC packaging and reliability and also failure analysis. And of course, all of that wouldn't be possible without a great metrology, which all the tools would be supported by the presence of the CSS&T Institute. A little bit more on the NanoIC project structure. It's a very large project, as you can imagine. We have 10 work packages, part of the first one, which is clearly the management one. We do handle, of course, the whole infrastructure via work package 2 and 3, so the tool installation, qualification, the procurement, and so on. And then, of course, we go towards more the R&D pillar, which are covered by work package 4 to actually 7. So we first develop a process in our clean room. We embed them in larger modules that are then how part of the processes are taking place in our fab. And then in work package 6, we work on integrate and platformize those modules towards more mature flows that will be then ready to be shared with the pilot line users. All of these efforts, actually, they streamline into the work package 7, which is the PDK definition. Here, we take all the learnings that happen in our fab, and of course, around using our simulation and our EDA models and so on, and we put them in a valuable PDK. At the moment, they are called path-finding PDK. We offer already since almost 2 years. We will go into detail into a moment. All of these services are actually made available to the public through the Access work package, which is the number 8. And then, of course, overarching all these efforts, there are the work package 9 covering dissemination and European outreach, and the work package 10, the full education and skill development, which, as I already mentioned, has an enormous importance in Europe, and I'm sure it will cover even more scope in the future. As just mentioned, in the pilot line, we enable early exploration of the technologies that we are developing. And to do that, we offer 2 types of PDKs. The first one are called design pathfinding, and second ones are called system exploration PDK. The design pathfinding PDKs are in design environment where students, people coming from academia in general, but also from private industries can actually experiment all these new technologies that we are developing, and tools, so 2 nanometer, A14, down to CFET architecture, and so on, and understand design trade-off, the architecture flow, or the whole design flow, and make sure that they understand all the technology capabilities that are today available through the NanoIC and will be in the future available in foundries, and as we see already today. These pathfinding PDKs are not directly linked to silicon wafers, to physical silicon. That happens with system exploration PDKs, which as of today are not yet available because we are still working on consolidating our process flows. And of course, that will also streamline into more mature PDK that in the upcoming months and phases of the project will enable users to really design and fabricate devices in the pilot. We need, as I said, to build a skilled European semiconductor workforce. This is fundamental, and that will be the winning game that we need to play in the upcoming years. To do that, the NanoIC Pilot Line enables PhDs, workshop, internships, expert courses, and we will give ample coverage in a minute when we go to work package 10. These initiatives are fundamental in Europe today because we need to extend and expand our knowledge on these technologies, which are partly even under development, but despite that, we can still introduce to that all the interested players can be even master students already interested in these technologies, and we can do that in the NanoIC Pilot Line. What do we do practically? Well, all of you probably have seen a picture like that, or a parent, somehow a relative of this picture. This is how do we envision in the future what is called actually a chiplet architecture. So a destructured system on chip separated in different modules. In the pilot line, we are developing different modules covering different areas of this chiplet. We work on the advanced logic, the memories, and the interconnect, which represent a little bit how we do make sure that all these different components can talk together. Why we need that? Well, today we are seeing already, actually since already a few years, that scaling down is not the only option, and actually is by far today bringing us towards what we call, for example, the memory world. We need to find alternative ways to create new and more powerful and more efficient system to, for example, perform high performance computing tasks. These are the technologies that we are looking to be developed in the upcoming 5 to 10 years. Some of them are already available today. Some of them will be more consolidated. Here at Imec, we have envisioned that as an electro-optic system. As you see here, there is an active silicon photonic interposer, but of course, this is just one version of the possible technologies. Today, there are several variants. NanoIC focuses on developing the modules that enable the creation of such structure. What are those modules then? Well, as I just mentioned, advanced logic focus on virtual PDK, nanosheet targeting 2 nanometer. These are gate-all-around transistors. A14, A10 to the CFET architecture, which is a completely different type of transistor architecture, stacking NMOS and PMOS, one on top of the other instead of laterally. All of that enabled by high-NA EUV and our collaboration with ASML, which is also a big sponsor of the project. The second big pillar of the NanoIC technology is represented by the novel embedded memories. Here we work on spin orbit torque memories and embedded DRAM memories together with 3D memory platform. For these technologies in the upcoming future, specifically for the DRAM, we will offer also fabrication services. Same holds true for the advanced interconnect, which today is getting a lot of interest from all the stakeholders, because it represents an incredible opportunity to combine chips fabricated using different technologies, optimizing the cost in one single element, which has all the capabilities at once. At Imec, we work on die-to-wafer hybrid bonding technologies, fine pitch redistribution layer, and silicon interposer. All of that also sided by integrated 3.5 lasers. Also for these technologies, in the upcoming future, we will offer fabrication services. Last words on my side. This year, 2026, we were already, as of 2026, we were already offering N2 PDK, but since a couple of months, we expanded the offer to include also A14, EDRAM PDK, and advanced interconnect PDK, covering die-to-wafer hybrid bonding and fine pitch redistribution layer. With that, my part actually closes, and I'd like to give the stage to our colleagues from the R&D team, I guess starting from the advanced logic. Perhaps Yasser can share, and for any question, please, either in the chat or Pierre, I don't know if we want to already open some question now. I'm here.
I think it's better if we leave the question for the end, maybe, so we can go on. So we can save the question in the chat and then discuss, but if you prefer, up to you.
Up to the audience, guys. We are here.
Yeah, let's move on with the presentation. Yes, please.
Yeah.
Okay, then I can start. I hope everyone is hearing me well.
Yes, yeah, we can hear you.
Okay, so let's start with the scaling, how things are happening. So we have been happily scaling and basically increasing the transistor density for a while, and pushing the number of transistors within the dies more and more. At the FinFET level, when we reach or after the 20 nanometer era, the FinFET had to be supported by DTCO, which is Design Technology Co-optimization. And this co-optimization basically helped us even drive the density according to the Moore's law predictions. So we are trying to still push further, go ahead with the scaling, and more what we see is that we have to basically get involved in system level discussions and do system and technology optimization, build up new devices, is to basically get back to the Moore's level of scaling. And if we look at the technology roadmap, this is an Imec technology roadmap where you would see that we are going through different kind of devices. Actually, there are 3 tiers that we touch upon. We continue doing dimensional scaling. We continue evolving devices and materials, going through different kind of structures, from FinFET to nanosheets, gate-all-arounds, to CFETs, to new devices in the future, far in the future, and also looking at context-aware interconnects. So doing efficient routing, doing placement that is context-aware and design-aware. So this is a roadmap proposed by Imec, but what basically pushes us to go from node to node. How do we define the technology? The basic premises for that is that we have to look at the figure of merit, which is power, performance, area, and cost. For a technology node, you have to look into the area, the logic performance, their dynamic and static power consumptions, memory, its performance, its power consumption, the overall cost. And more and more what we see is that for different applications, whether it's mobile, server, AI, all of them would require different type of optimizations, and these optimizations would lead into different kind of basically overall optimistic or optimized node for each application. But traditionally, what has been happening is that the digital part of your designs and your circuitries have been scaling with respect to the area, and that has been the real pusher in that sense. So in order to build that, you have to look at the transistor. So traditionally, the basic transistor is a 4-terminal device where you have a gate, you have a source, you have a drain, and LG was defining your technology. And the smallest circuit that you could build was a NOT gate, which had an opposite input to output conversions, and you would build a schematic out of it. You would basically try to charge and optimize output node and discharge an output node based on the input, and you would get your input to output VD curves. And when you try to lay out this so that you could fabricate it, you could basically make a template out of it with respect to the contacted gate pitch. So you had a gate pitch, you had your metal pitch, and this would give you your horizontal and your vertical spacing, and basically give you your first order of area. And if when you look at any product, you would see that within that product, you would make your cells, you would place them, you would route them, and that would basically then be fabricated. And if you look at the fabrication cross sections, you would see that at the bottom, the tiniest one are your transistors, then your middle end of the line, then your back end of the line, which would be gradually becoming larger. So this is your digital flow. and what was enabling that, if I try to plot this thing into CPP, which is the contacted gate pitch and your metal pitch, I can basically plot all these nodes with respect to the lithography limit. So for 193i, this is the single print limit, and within those limits you would see these nodes that come up in there, and then you have EUV limit nodes where you have certain nodes that are popping up. And now most of the era that we're looking at, it's somewhere in the bottom over there, and we are trying to mix match, and that's the current era where a lot of nodes are popping up because the overall scaling is slowing down. So we have to push these nodes with more optimization with respect to the device, with respect to the system itself. And in order to capture all of that, you have to basically develop the PDKs. And what are those PDKs? Well, basically a PDK stands for a process design kit. So you basically try to, it's a tool where you want to go from the technology and design, and you want to model everything all the way to the design and be able to fabricate that. So this gives you the environment where you can structurally construct your designs. And looking at what is available currently, you would see that the foundry PDKs are somewhere around nodes and 2 nodes, and they are usually available to the ecosystem once the technology has reached a certain critical manufacturability. However, this is quite restricted, and you have to sign a lot of NDAs to, and that creates a high threshold for academia to access those. So academia is lingering behind these foundry PDKs, and they are basically operating like 6 generations behind. So the idea over here is that Imec, where we are looking at the technology nodes that are ahead into the future, we try to create virtual PDKs with some assumptions and try to make them open access so that the academia or people who are interested out of academia can do some experimentations on it. So if you look at the overall structures that we have to enable this, what we try to do is we do quite a lot of device modeling based on TCAD, physics simulations. We try to create a lot of models out of this. In parallel, what we also do is we try to make templates and cells. We try to create libraries, and we try to characterize those libraries based on the models, so we get a complete holistic library that is electrically testable. Plus, we also look at the memory, and we try to create memory SRAMs cells, and we want to create the compiler so that we can make memory units within those technologies. Additionally, we have our physical design infrastructure. We take these libraries, we try to do a lot of place and route experiments based on different IP modules, and do evaluations of these modules. And this gives us the complete infrastructure where we can test our initial hypothesis for the technology that we are looking into. So the current 2 options that are readily available for people to use are N2 and A14 nodes. And within N2, we have 2 options where we have a front side power connected node, and we also have a backside power delivery mechanism for the N2 node. And when we go to the A14 We have another version where we try to directly connect to the backside. So this is a digital PDK. This has full digital flow enabled in Cadence and Synopsys. We have 3 flavors of devices. And for the N2, we also have pre-categorized single port SRAM macro instances. So why do we go to the backside delivery network? The reason we do that, if you look at a normal silicon designs, you will have a silicon wafer, you have your transistors, all of your metallization is on top. But if we try to bring the power delivery network from the backside, we would basically etch away, grind away the silicon, and we will build the metallization from behind to deliver the power. The benefit is that BSPDN basically reduces on-chip IR by an order of magnitude. It helps us scale the chip area. It also helps reduce the complexity of the front end of back end of the line. And in the future, what we would see is that if we go in this direction, it will also make life easier to do wafer on wafer bonding. For example, if you want to do memory stacks onto a logic. So that's a promising technology leeway that we would like to explore. And now looking at the very specifications of the N2 and A14 that are available, so you would see that the difference between the gate pitch is quite minute. N2 is 48 and A14 is 45 nanometer. The metal pitch is also a very minimum difference, but with this kind of scaling boosters and scaling optimizations, what we achieve is a standard difference in the standard cell height. And that basically helps us in reducing the overall footprint of the standard cell height, the standard cell. Additionally, the main difference between these two is the through silicon via that we were using in N2, and for A14 we actually go and directly connect from the device from the backside. So there is an additional via that basically comes and connects in. One more difference that you would see right now is that in the release PDKs, for the SRAM, for the N2, we have 29 SRAM macros. For the A14, they are not, but in the future, we'll also make them available. So looking at the standard cells, this is a comparison of A14 area with respect to N2. So we look at all the cells that we had created. It's a library of 150-ish cells. What we see is that the area reduction cell to cell comparison shows an 18 to 20% gain in A14. And when we did our PNR experiments on an ARM core with CPU 53, what we saw also matched. So the area reduction was 18%, and we also could gain 5 to 7% in power. So overall, this is the comparison of the nodes that we already have right now, and Imec and are open to be accessed and to do experiments. And thank you for listening for now. If you have questions, you can basically put them in the chat.
Thank you, Yasser. I think we can proceed with the next speaker. That should be Sarah or Roxandra.
I'm not sure. Maybe I take over? What's the
Mari,
agenda?
yes.
Yeah. Okay, perfect. I will take that screen.
Sorry.
So no problem. So my name is Marie Garcia Bardon. Can you see my screen?
Yeah.
Coming up. Perfect.
Yes, we can see the screen.
Perfect. Good afternoon, everyone. So I am also with Imec. I'm department director here at Imec, and I happen to be also the Work Package 7 lead for the NanoIC project. So as Giuseppe explained, Work Package 7 is for PDK production and test chip design. So the slides that was also produced with Attilio, or program director active memory at Imec. So I will zoom in memory. So after I covered logic, shifting to memory, a little bit of context on today's systems and application. If we need to choose a keyword, could be AI, but I will pick data. So all across all applications, from data centers, automotive, mobile, IoT, XR, because of the massive use of AI, we have a massive amount of data to deal with. And that has several consequences. So data needs to be computed fast. Yes, that's historical, but mostly now you need to store this data somewhere and you need to access it efficiently. So you need to move it efficiently between compute area and memory areas and optimize this back and forth. So that's opened a totally new game for technology innovation and architecture innovation. And that creates a lot of opportunities for innovating in technology. And we also see the emergence of a lot of domain-specific architectures and specific solutions. So what we really want to highlight is that today's systems are mostly memory and interconnected limited, not really computed limited anymore, although compute also still needs to take more and perform better. And the target here is to have large memory close to compute, so to have high capacity, high bandwidth, low latency, and low power. So if you look at the traditional system, you would have at one side your processing units with on-chip memory, so the SRAM, and further somewhere you will have your DRAM, so your standalone RAM. So today, in today's system, the on-chip memories hit a capacity wall. The SRAMs are not scaling anymore sufficiently, or not scaling at all anymore, so you cannot scale the bit cells anymore. And if you are off chip, you are bandwidth limited. So you have the bandwidth wall because you cannot transfer efficiently enough through the interconnect your data. And you also have a capacity limit. So now what is happening in the technology innovation world to address these problems, these bottlenecks? At one side, we see a strong development of HBM memories, so high bandwidth memories that are basically DRAM stacked on top of each other using hybrid bonding. We also see an alternative route there that is 3D DRAM. So it's basically monolithic DRAM stacking. So it means you do it inside one process flow, not using hybrid bonding, but doing the deep edge within your chip. And if we look at on-chip solution here on the other side, there are also a lot of different technology options on the table. One option is to integrate, embed your memories in the back-end of line interconnect of your chip. So you have your front end with your CMOS, then you interconnect with metal routing, and inside this metal routing, we will start placing what is called embedded RAM. It can be IXO-based, and I will particularly focus on that technology here. It can be magnetic. There are also ferroelectric solutions and other solutions. Another option is to attach another chip by hybrid bonding on top of your processing chip. And here again, you can have all type of technology solution to enable this extra memory. This can be even an SRAM, an extra SRAM. That's the Vcache solution, for example, from AMD. But you can have also these new technology solutions that will be made on a separate chip and then bonded on top. So now, what are we doing inside the NanoIC project? So inside the memory enablers, we look at three different solutions to address these memory bandwidth challenges. The first one is 3D memory is monolithic 3D, so that I mentioned. So that's being developed on the technology side, but there will be no PDK attached to that inside this project timeframe. We look at magnetic solutions, specifically SOT-MRAM platform. Initially, we thought this one will develop sooner. At the end, there are major technology challenges. In particular, the switching currents are too high. So at the moment, this is still early stage development, technology improvements. And now the strong focus is on the embedded DRAM IGZO-based platform that is showing great promise to perform well, and that will target the highest technology readiness level in the project. So the memory is the strategic component of your CHIPS Act project in general. So it's inside NanoIC, also inside FAMES, you have memory, embedded VM Faro-based, 1T1C. There are also startups that have sponsoring from multiple stakeholders and EU, like FMC on Faro NVM and vertical compute, these two really targeting extremely high density vertical memories on chip. Now, zooming in on the embedded DRAM question, what is the IGZO-based DRAM? If you have some background in DRAM, you know that a DRAM is a 1T1C system. So you access through a transistor to push charge in a capacitor. And in a DRAM, a traditional DRAM, the capacitor needs to be large enough to store enough charge and to keep this charge at least 64 milliseconds. And because it needs to be very large on a small footprint, the aspect ratio is immense. Now we are talking about technology that will be capacitor-less. So instead of having this very large capacitor, we move to a system where we have two transistors. So the capacitor has disappeared, so it's a 0C, and now we have 2T, so it's called 2T0C system. And actually the storing charge is now just at this connecting node between the two transistors. So this capacitor-less eDRAM is a game changer in the memory ecosystem for multiple reasons. First, the IGZO technology, so the material IGZO is back-end of line compatible, which means, as I mentioned at the beginning, you can process it on top of your normal CMOS logic because it's low temperature. So you can integrate it in your backend. Because it's capacitor-less and it's very compact and the transistors are laterally stacked, you can 3D stack. So we could make them different layers on top of each other and have very dense configurations. The IGZO transistor itself has extremely low leakage current. And that's why we can do the storage node, because that allows very long retention time. Basically, it will take very long before the charge is completely leaked out of the retention node, so of the storage node. Because it's charge-based compared to other non-volatile memories like ferro and magnetic, it's fast and it has a long endurance lifetime. Typically, ferroelectrics will get tired earlier. The fatigue will start early. And then because of the configurations that I will show you, you can engineer your write and read transistor separately. So there is a lot of benefits. Of course, there are also a lot of challenges still to be addressed and improved. Now, does it work? Because it looks very promising. So the IGZO-based DRAM functionality is successfully proven by Imec in several years. So the concept has been introduced in 2020. And since 2020, you see that the IOF ratio and the retention time have massively improved. It's demonstrated on 300 millimeter wafer for functionality down to a gate length of 25 nanometer. So dense enough for the application targets. For a 4.5 hours retention, of course, if you compare to SRAM, it's a technology that will need refresh if you are a designer, but compared to DRAM, it's a very good retention. So we are sitting in between the two worlds. And the endurance is higher than 10 to the 12 cycle, which is also good. So all this is promising. Now, the results I'm showing you are for a configuration where your two transistors are sitting side by side so far. So they are in the same plane and they take quite a lot of area because they are side by side. So inside the NanoIC project, the idea is to boost density and increase the technology readiness level, but increasing the density by stacking the two transistors on top of each other. So that means we decrease the footprint of the overall bit cell, we increase the density, and because they are now on different layers, you can, as we mentioned, improve your write and your read separately. You can customize, engineer them completely separately in your flow. Now, after that this work has started at Imec, we see implementation spark the interest of academia and industry with various 2T0C architecture and different structure and material proposed over the last 5 years in different research centers. So in particular, in a collaboration between Stanford and TSMC, and so there is foundry interest for these new technologies. Now, how will this technology be accessible inside the NanoIC project? So that's like Giuseppe explained through the process design kits. So a process design kit is just a tool for designer to play with the technology and create systems. So a design kit contains electrical model, a design environment, documentation, and we are providing training. There is one next week for EDRAM on Tuesday. And then we add to that IP design library. Yes, I commented for logic, the IP libraries are quite extended, standard cells, SRAM macro. Here, we start with small arrays. Gradually in the project, we will add the ideas to converge to a full macro, but also give access to simple bit cell for people to do non-traditional circuit design, like neuromorphic. So these are hybrid PDKs since we are talking about a technology that's integrated in the backend. So at the moment, the PDK is a memory add-on that you will combine yourself with a standard CMOS PDK. So at the moment, there is no standard CMOS front-end distributed. So if you remember, we integrate the memory on top of a CMOS. It means that the CMOS foundry process is stopped around M5, M6, M7, depending on the versions we have. And then we add the backend of line layers that contain the memory elements. And this can be further combined with interconnect add-on that will be presented by Nicola later. So at the moment, we will produce this distribute solely this memory layers add-on that you can then instantiate with whatever standard CMOS PDK you have to do schematic simulation. Later in the project, we will enable layout simulations and then provide also the front-end technology. So this means we really work in a system of PDK version that follow the technology maturity increase, starting very early. Now we have the proof of concept, basically. So we released recently a first PDK that enables schematic only, that is already calibrated on the early silicon device data. But you can already experiment on the concepts, learn on this technology and do some pathfinding. There will be a second version that has more hardware calibration that enables the custom layout where you can do a bit more architecture exploration. And then later on, more statistical data, first validated IP block, where we are already talking about more de-risking on the technology. And then later, but after the project, NanoIC project completion, of course, the intention is to get to a PDK that will at some point enable prototyping. But we are still really early. I will show you the timeline afterwards, but actually it's here. So right now we have optimized the planar version side by side, and we are optimizing the stacked implementation of 2T0C. Now we move to the first PDK release, and now we are really working on designing characterization arrays for tape-outs that will happen in the last quarter of 2026. And then once the chip is back, we will have much more data, also high-speed on-chip testing to have full validations of this technology. And we will produce then new PDK with early data, and then a full PDK at the end of the project that will be our projection at a more scale node. So this characterization array, we are still on top of a CMOS foundry 40 nanometer, 40. While the projections will target around 16 nanometer, 16 foundry dimensions. With this type of dimensions, because of the high density of the memory, you are actually competing with very advanced SRAM. So we gain 4 or 5 technology nodes in terms of memory density. Even if the CMOS front end is relaxed, the memory density has extremely high benefits. So 3 takeaways. You saw I really focused on the EDRAM because it's a high TRL memory technology in the project. Capacitorless EDRAM is really appearing as a potential game changer for memory scaling and a strategic technology if we manage to push it to the full potential. The technology is today successfully demonstrated on 300 millimeter wafers using scale transistors, so 24 nanometer gate length. The NanoIC project aims at increasing this maturity further. We will demonstrate first a 64 kilobit array, and then the plan is to tape out megabit demonstrators in 2028. That was it on my side.
Perfect, thank you. I think the next speaker should be Nina.
It's actually Nicolas.
Okay, sorry.
No problem.
Good afternoon, everyone. So my name is Nicolas Fontano, and I'm leading the technology demonstrator team in Imec, focusing on mainly interconnects. And I will present you also the advancement on the advanced interconnect PDK that we're developing, which will be used for prototyping on these pilot lines. Maybe just to give a bit of historical background, why we do this. So if we come in the 90s, we have started to see system in packages. We try to bring all the components closer to each other to improve the form factor, but also the performance. And that's where in the year 2000s, we have started to see RF modules integrated also with the advancement of smartphones and systems like this. Then a bit later, we have started to see silicon interposers. Silicon interposers have been seen on FPGAs, but also on high-performance compute, which has started to increase significantly in the data center as the amount of data that has to move through the net was increasing. And still, we wanted to have more and more inside the same package to increase the compute capacity. We have seen this ultra-high density RDL, this fan-out wafer-level package, because there was a scaling of the CMOS node, but at the same time, the package doesn't scale that much. So that's why we have seen this wafer-level packaging happening. And then the next step was kind of logical. If you start to use all the tricks to use the 2D plane, at some point you have to do 3D. And 3D has started to happen with images, where we have the pixels combined with the memory and the DSP, and in a bumpless fashion, so what we maybe call today hybrid bonding. Images was probably the first product that has adopted that hybrid bonding technology. And this is something we actually continue to see. We want to bring all the modules closer and closer to each other to increase the throughput, the bandwidth, and especially now with AI, where there's a tremendous amount of data that needs to flow between the memory and the compute. We want to maximize the capacity of the memory inside one package. The package starts to be bigger, and the amount of interconnect is also rising. And in the future, we will start to see really logic on logic on logic, system 3D. There's still many challenges in terms of thermal, but we'll come to that. So when it comes to 3D system integration, there are many challenges. Of course, you want to cool it. As you try to pack more and more system into the same package, it becomes the heat needs to be dissipated. This is one of the challenges. You need to bring the power that was also explained briefly in the advanced logic PDK, where we have these backside power delivery network or the direct power rails. There's a different technology to bring the power from the bottom to the transistor and to save space for routing at the top. But also, when you start to do this, you need to connect both sides of the silicon. And there we need through silicon via. Through silicon via, the first dimension were 10 micron in diameter for 100 micron thick. Of course, if you want to increase the density of connection, you need to scale them. That means scaling the silicon and scaling the diameter of these TSVs. And especially for this buried power rail or this backside power delivery network, the TSV needs to scale significantly in the micron scale or even below in the nanometer scale. At the same time, you want wafer to wafer or die to wafer high density interconnect. This will be helpful in the future to do logic partitioning. So that means that you will distribute your logic compute between two dies and assemble them on top of each other with a high density interconnect. Today, we see pitches in R&D that goes for 400 nanometer, even down to 200 more recently, of interconnect, vertical interconnect between two wafers. But wafer to wafer is good, gets to very fine pitch, but that means that each of the die needs to have exactly the same size. So they will still have systems that have chips that have different sizes, and that needs to be combined in 3D fashion. And that's where die-to-wafer hybrid bonding start to happen. We want to scale the micro-bumping. Maybe today we are in the range of 40, maybe 25 micron down to 20, or even below to 5 micron, which is probably a limit. And then to even scale further, we use the couple-couple direct bonding or the hybrid bonding to scale that even further, as you can see on this plot, on these images here. But at the same time, as I said, it's good to use a third dimension, but you also have to scale in the XY plane. And that's why silicon interposer, reconstructed wafer, high density RDL are still major technologies that are needed. And these are the technologies that we want to enable through the NanoIC Pilot Line, especially for the hybrid die-to-wafer hybrid bonding and the high density RDL. So this is just an example of what is the 3D interconnect landscape and how we pack different technology together. You have the package on package, which is very that you see in any mobile system, 2.5D multi-die. This also exists maybe in edge devices or advanced HPC. And then you have the 3D IC stacking. And as I said, in the future, we'll have like 3D IC with partitioning, also the CFET, and what we call a Imec CMOS 2.0. So there's a bunch of technology, as I said, that needs to be developed in time to get to these advanced packaging systems. Now let's focus a bit on what is the pilot line for IC1 and IC2. So this is a picture that you have seen also in the presentation of Giuseppe. There are a bunch of XPU. There could be a laser for silicon photonics as well. There's an HBM, fiber connection, and some embedded die that could be active, passive, which will have RDL and hybrid bonding. If you focus to IC1, which is the hybrid bonding, this is where the PDK is playing a big role here and what we offer. We offer die-to-wafer hybrid bonding and oxide embedding with true oxide vias. So what is inside that PDK? Well, you will be able, as soon as the pilot line is launched, to do prototyping down to 2 micron pitch die-to-wafer hybrid bonding with an oxide field and with what we call TDVs, through dielectric vias. In that sense, you have a connection from both sides, but also pass-through. So you would have TSV through your active die or your bridge, and also a direct connection from both sides. This is part of the NanoIC. It's also very important to understand that this technology is quite complicated, and today, unless your name is Apple or one of the big ones, these technologies are unaffordable and you cannot even access them. So that's what we would like to enable. I would like to dive a little bit into the details of what die-to-wafer hybrid bonding is, just for your education. So you start with a wafer where you create hybrid bonding pads. Something very essential to understand is that hybrid bonding is a very complex technology. And the reason why is you need a wafer that is very flat. Just to give you a common sense, you need less than 1 nanometer variation in thickness over 1 micron of distance. So there's a factor of thousands here between both axes. You also need to singulate this die, and by singulating, they need to be clean and pristine, and especially at the hybrid bonding surface. So that's also a very complex dicing process, which doesn't use blades, but a litho process. Then you take a die, you flip it, and you place it on the target wafer. Obviously, if you want to have 2 micron pitch, you need a precise alignment, which is not helping in the complexity. But ultimately, you will end up with a clean system, hybrid bonding, no gap between the 2 chips. And if you even do a cross-section, it's difficult to identify where that interface is located. So it creates like a monolithic block of 2 silicon chips. This is an example of an illustration of what I said just before, where we have several die. These black dots are chips that are hybrid bonding on the wafer. And you can see here, unless I tell you that the interface is here in the middle, you would not even know that the chip are actually bonded on this layer. And you see that you have very clean connection between the top and bottom, and a 2 micron pitch. So this is for hybrid bonding. Hybrid bonding is very good. This is excellent for 3D applications. But there is also other type of application where you would need lateral interconnect, and that's the RDL. So to basically explain, to integrate several chips in a 2.5D fashion, as we say, there are mainly 3 technologies. You have the silicon interposer, where you have a silicon chip, passive, only have back-end of line and TSV, that is able to interconnect the 2 SoC that would be, for instance, stacked on top. This is also what is called CoWoS S, or silicon interposers in general. A more less costly approach is to use silicon bridges, because you don't need fine pitch connection between these 2 SoC everywhere. So the industry has come with what we call fan-out wafer level package, or EMIP from Intel, or CoWoS L from TSMC, where you use a polymer-based material on the relaxed pitches that would bring the output signal, the power, to the SoC. And for the connection between the 2 SoC, there you use a silicon chip, which can have very fine pitch. The problem, or maybe the challenges with that technology, is that you have to bring one of these bridges inside the polymer. There's a CTE mismatch. So that means that they will expand with temperature differently, because one is silicon, the other one is a polymer. And it's very complex when you start to scale the system to many SoC integrated, and you start to have many of these bridges. So Imec has developed a fine pitch RDL process, which is a polymer based, that can get to dimensions that you have on a silicon bridge. So you get rid of the silicon bridge, and you have a monolithic organic substrate here. So diving a bit into the detail, what is the technology under the hood? Currently the PDK will have 2 metal layers, but it's planned to be extended. The dimensions in the exploratory PDK is 1.3 micron pitch. 1.3 micron line width and spacing. There's obviously no TSV needed, because in practice you would release that layer and put your BGA balls. So that's also an advantage from that perspective for signal integrity and power integrity. At the same time, we want to offer a fine pitch bumping technology about of 20 micron pitch, which is currently not fully available in the industry. Just also to give you a bit a glimpse of what could come next and what we actually work on in the R&D program, we make 500 nanometer line within spacing. But what we're going to offer on the NanoIC is indeed this 1.3 micron line within spacing, and in the future probably this is going to scale. The main advantage, which I did not mention for the fine pitch RDL compared to other type of RDL technologies, is that one of the drawbacks of the organic substrates is that the via pads are extremely big compared to the lines. They create congestions in vertical routing, but in the way we do the process, which is a Damascene process on that RDL, we can have vias that have the same size of the line. So that means that the congestion that you have in standard polymer-based material goes away. Because you use a processing flow that is very similar to the back end of line of silicon die. So to conclude a bit, what is part of the PDK, just to let you know, today we have released the alpha version, so version 0 as we call it, of the PDK. They're mainly used for exploration and discovery of the technology and what is the offering. So the PDK contains a design rule manual, a design environment for Cadence Virtuoso and 3D IC. There's technology left file for automated place and route, and DRC checks. On IC2, there's extra content, LVS, system LVS. So system LVS, for those who don't know, is used for connectivity checks when you do 3D assemblies using EDAs. And also we include standard PECs for parasitic extraction. I just want to show you what we have done with the PDK is an example of a routing of a UCIe interface of 16 gigabit per second, which we will be able to route on 2 layers. And this is available today through the Europractice website, but I think Nina is going to talk about that later. So that's it for me. Thank you very much.
Thank you. Let's continue with the next speaker.
So I guess it's my turn, right?
Yeah. Yes.
You hear me well? You see the screen? All good?
Yes, we can. Thank you.
Good. Okay, I'll get jumped. So good afternoon, everyone. You've just heard a lot of marvelous things about what NanoIC is capable of offering. My role today is much simpler and more straightforward and basically covering the practical side of it. I'm going to talk about how you as a user can have access to the technologies offered by the NanoIC Pilot Line. Before jumping in, I would like to just take a second to introduce myself. My name is Nina Bazazian, and I'm the project leader for NanoIC Access and Outreach. So basically the contact point that you need when it comes to access. Here in this schematic, you can see the processes leading to access to the NanoIC Pilot Line, and I understand that at the first sight this may look like a bit of a complex flow, but in reality for you as a user, it starts with something quite straightforward. You just contact the pilot line. And everything else that you see in this schematic is mostly what happens on our end to make sure that your request is properly evaluated, assessed, and hopefully turned into real collaboration. So let's go through this step by step. Here, the first step is simply, as I said, contacting the pilot line, so reaching out to us. On the right-hand side, you can see a snapshot of the NanoIC website. So the access section on our website, where is basically the main platform where you can contact us. What is important in this point is that you don't need to have a perfect proposal. You don't need to know every single technical detail. What we need to understand is only what you're trying to explore. So whether you're interested in having access to a pathfinding PDKs, or a system level exploration, or maybe you're a tool manufacturer and you want to explore how collaboration can happen on that front. These questions, they are essential because they actually lead us to choose one of these services. So between the pathfinding PDK, I'm going to take my laser point system level exploration and the tool manufacturer. Here I wanted to take a moment to talk about the content of services, but thanks to the very thorough presentation of Marie earlier, the distinction between pathfinding PDK and the system exploration PDK really became clear. So in short, the available pathfinding PDKs through the NanoIC Pilot Line, which are built on the predictive models of future technologies at Imec, are based on these Imec N2, A14, A10, and A7 logic nodes. So they are typically aligned with rather lower, let's say, TRLs, and basically it makes them very suitable, very ideal for academic benchmarking and the early stage DTC, or design technology co-optimization, and the explorations that it brings. Whereas when it comes to the system level exploration in NanoIC, these are designed to support more of, let's say, hardware prototyping and system level innovation at more advanced areas. So particularly they are for future demonstrations of NanoIC Pilot Line, which would start very later in the project, around, I would say, mid-2028 and onwards. And last but not least, when it comes to the tool manufacturer bucket, it would be, the collaboration would take very tailored path, because it really depends on the needs of the customer or user in this case, and the capabilities of the pilot line. The next step is about the documentation and assessment. So here it becomes a bit more specific depending on the selected services. For the pathfinding PDK, the user proceeds with submitting the DKLA via the email link that is available on the Europractice platform. And in the future, this will be implemented through a dedicated user portal. But for system exploration and tool manufacturers, this is actually a kind of a multiple stage verification process. And this verification assesses different fronts when it comes to, for example, the export control and strategic compliances, to check whether the compliance of the potential user with the current export control regulations are in order, and business and strategic and IP considerations. But very importantly, to assess the technology match with the pilot line capabilities, including the timeline and tool usage, and again, the need of the user. The next step is about the time that it takes to review those documentations. So at this stage, for the PDK flow, the so-called DKLA, so the design kit license agreement review is performed. It's done internally by the export control and the legal team. Whereas for the system exploration and tool manufacturer's flow, user will receive a feedback on the outcome of an internal, let's say, assessment, we call it internal strategic assessment. And this process may require multiple dedicated calls, not only one, to make sure that different aspects of this request and of the capabilities being discussed are clarified, and we find questions, and the answers, the questions answered. It might not be very relevant to the audience of this webinar, but worthy to mention that for entities not participating to Horizon and Digital Program, there is an additional verification stage via DG Connect offices, where the access team submits dedicated requests explaining the added value for the EU and the pilot line, and then it would, let's say, take an additional parallel path when it comes to the intake process. The final stage of the intake process is when the approval is granted. So once approval is granted for the PDK flow, Imec creates an account in the internal database. It's called Querio for the PDK and for the corresponding DKLA. And this is, again, in the future, will also move to a dedicated user portal. For system exploration and the tool manufacturers, after successful assessment and, let's say, acceptance of the initial initial collaboration terms, contractual negotiation will be started between the pilot line lead partner and the user. And the outcomes of these negotiations can include access to PDK, assess the process modules and access to the process modules, design applications, or even participation in potential NanoIC technology shuttle. But it's basically let's say, the initial project planning. So with this, I wrapped up let's say, the intake process. And here I would like to share with you a few numbers on actually how we receive this, the request when it comes to the access. So far, more than the N2 PDK, the N2 PDK was released, and more than 50 institutes requested access to this PDK, of which 38% were European entities, around 21% from Asia, and the rest of them, around 30, non-EU based entities. And the progress for these EU-based entities, as I mentioned earlier, is now agreed with the DG Connect, and it's being followed on that parallel path. Very briefly, so yeah, the PDKs that are released in this through this framework are A14, EDRAM, die-to wafer hybrid bonding, and redistribution layer. The last slide that I wanted to share here, is about metrology in the pilot line. And I think it's very clear to all of us the necessity of having the variety of tools and techniques of metrology when we talk about physical inspection and fabrication in the semiconductor field. And this is actually one of the very significant goals of NanoIC Pilot Line, to make sure that the whole European ecosystem have this, let's say, smooth access to these offers. And so through our website on NanoIC, there is on the section of access, you can find this metrology dedicated page for metrology, which actually works as a, if you wish, one-stop shop. There is the capabilities of all the partners of the consortium is they're listed there. So you as a user, you can go over it, and based on your needs, you choose which one to continue your research with, and then at that point, basically it's going to be a direct collaboration between you and that particular, let's say, owner of the metrology tool and technique. It's a unified platform offering several analysis and then let's say fabrication tools, and the goal was basically to simplify access to the metrology tools for startups, universities, and basically everyone in this ecosystem in Europe. So that was my last slide. I explained quite quickly how a typical access can be taken in this project, and with this, I hand it over to my colleague Ruxandra.
Hello,
Thank you very
everyone.
much. Please, Ruxandra.
Oh, yes. All right. So it's up to me to give the last presentation of the webinar, and I will focus on the part of education and workforce development on the offer that we have within NanoIC. My name is Ruxandra Flore. I'm a project manager here at Imec, and I am responsible for the technical trainings offer within the NanoIC Pilot Line. So Giuseppe already explained quite well the activity clusters of the pilot line. One of these four is the one on education and workforce development, and there we have quite a comprehensive offer at the moment. Of course, the PDK workshops, which are directly linked to the technology platforms introduced by Yasser, Marie, and Nicolas, but we actually have quite a good range of other offers as well, of other trainings as well, and other opportunities. So specifically, the NanoIC Pilot Line offers opportunities both for PhD students and for interns. There are the PDK workshops that I will introduce later on. We also have a range of seasonal schools, which we piloted last year. And we have an offer of expert courses. I will start with the opportunities for PhD students and interns. There's also a nice QR code there in the top right corner of the slide, so you can follow our, you can investigate our current offer. Imec has a wide range of research internships offering bachelor students, master students, and PhD students hands-on experience on premises, guided by our local experts. And these are internships that range between from 3 to 18 months. There's actually an internship called Right Now, and it will continue until the end of next month. We are not the only ones to offer internships, so our partner within the pilot line, Tyndall National Institute in Ireland, has their own offer of internships. They call them summer fellowships. And again, it's a very good opportunity to have hands-on research experience with experts in the field. These are mainly fellowships targeting researchers in Ireland. However, also limited number of places are reserved for students within the European Union. These are more lengthy, so fixed duration research projects lasting 12 weeks. and they are complemented by a workshop series. Since they are summer fellowships, then the applications typically open end of the year or in December. At the very latest, the next application window will open in January. Other than research internships, Imec also offers a comprehensive range of PhD programs. So these are PhD topics and theses that are supported and financed by Imec. And this is a very, very nice opportunity to do some groundbreaking research at Imec. Of course, the range covers the topics that are under investigation at Imec, but within the NanoIC Pilot Line, we also have specific topics that are related not only to the technology platforms, but some of them are on lithography, some of them are on algorithms. So it's really quite a good mix of topics there. It's also a very good opportunity to join our community of over 800 PhD students that come from more than 40 countries. So keep an eye out for the next window for PhD applications. It will open on June 22nd and it will close on July 8th. So we have the internships, we have the PhD programs. For students, Imec also organizes twice per year. One time in the spring and one time in the winter, the so-called Imec Students Excellence Days. So this is a one-day event where among the many applications that we have, a certain number of students are selected to come on Imec premises to see to get a feel of life at Imec, to get presentations from Imec experts, but also from the Imec CEO, to get clean room tours and various demos on site. So save the date, the next one is actually happening on November 25th. So this pretty much covers the offer for students in terms of internships, events, and PhD programs. However, students can also participate to PDK workshops. I will stop here to say that this, the access to these PDK workshops is not restricted to students. It's actually open to academics and it's also open to the industry because these PDKs have been discussed already in the previous presentations. They are a very good way to get hands-on experience with the PDKs that are released by the teams working on logic, memory, and interconnect. And it's also a very good way to get familiar with these technologies. The one on the logic technology platform and in particular the nanosheet PDKs, this training is our longest running one. We've already had 4 editions and up until this year they were exploring the N2 pathfinding PDK. At the beginning of this year, we have also released the A14 pathfinding PDK, and this gave us a very good opportunity to expand this training, to also cover not only the theoretical foundation of the A14 technologies on top of the N2 technologies, but also practical design strategies and implementation in the design flow. So these are these trainings have 2 components, which is also why they are spread on 2 days. The first day is lecture, so really good deep dive given by our experts on topics related to end-to-end A14 technologies, whereas the second day is a purely hands-on with the PDK. And it always happens at here at Imec. This year has been a very productive one because we didn't only release the A14 pathfinding PDK, we've also complemented our offer with the EDRAM pathfinding PDK. So this is very, related to the presentation of Marie. Like she mentioned in her presentation, we will have a training next week, Tuesday. Unfortunately, the applications have closed for these trainings, but we do intend to repeat it. And this is one day in which our experts will give lectures on not only the key foundations of NanoIC's IGZO-based EDRAM PDK, but also materials, design principles, potential applications of the PDK, and also a very nice deep dive into the functionalities of the PDK. So again, just like the nanosheet pathfinding PDK trainings, this is happening at Leuven, and we expect members of the academia, whether students or professors or researchers and so on, but also members of the industry. Last but certainly not least, this year we have also released the two interconnect PDKs, so on the redistribution layer, a fine pitch redistribution layer that Nicolas very nicely described, and on the die-to-wafer hybrid bonding PDK. This training is also happening next week. It's also first edition, and it directly follows the EDRAM PDK, such that we give the opportunity to our participants that may be interested in both tracks to come on site and to follow both trainings. This particular training is a one-day workshop. There will be two introductory presentations. However, let's say the meat on the bone, the bulk of the program consists of hands-on exercises with our in-house trainers on the two PDKs that I've just mentioned. And again, here we expect members of the academia and professionals there, so members of the industry. This covers the current offer of PDK workshops, which we are very proud of, and we are extremely happy to share these new developments with both the industry and the academia. But we do not stop here. As I've mentioned in the beginning of my presentation, we have piloted a new type of training end of last year, which are the NanoIC schools. So these are typically 2 days. We've already had 2 editions actually. One last November on the winter school, the NanoIC European Winter School or patterning, so on topics from CMOS processing, lithography, photoresist, mass technology, so quite a wide range of presentations given in these 2 days by our Imec experts. And we follow that with the NanoIC Spring School on advanced CMOS, so different topics, different deep dives on different topics of material science, characterizations, test structures and vehicles, and many others. And we were very happy to see that they were both not only full house, but also extremely well received. The feedback has been overwhelmingly positive on not only the events itself, but also on the quality of the presentations, on the technical preparations of our experts. In each occasion and after each presentation, we have had participants stay, ask more questions to the speakers, and engage not only with the speakers, but also with each other in the breaks. So it's also a very good opportunity to do networking, to connect with other experts in the field, with other researchers in the field. Again, here we try to have a mix of participants. The first one was, let's say, more of a mix. There we had both academia and industry. We had the same on the second edition. However, in the second edition, we'd really focus on attracting more students. Like Giuseppe said, it's very important to have renewed pool of researchers working on these topics. And in this sense, we wanted to make attendance to these events more accessible to students. So the approach we took in March when we had the NanoIC Spring School was to link it to the Students' Excellence Day. So these were consecutive events, and we did see that it had a positive effect. The success of these two events was very encouraging to us, which is why we intend to continue. Do save the date on November 26th and 27th for the NanoIC European Winter School. The details have not yet been published, but they will come within the following months. And if my sources are correct, it will be on memory. But the full program and list of topics will be shared in the coming months. So we had the internships, we had the PhD topics, we had the Students' Excellence Days, the PDK workshops, the seasonal schools. We are also rounding up our offer with expert courses. So these are the latest addition to our family of trainings, specifically the expert course on epitaxy, first edition. It will happen on the 10th and the 12th of, between the 10th and the 12th of June this year. Sadly, registrations are closed here as well. However, we expect that it will be quite popular, and we hope to repeat the event. It's not the only expert course that we have. We actually intend on rounding up our offer with an e-learning module. So work is already on the way. We expect to launch it to the public in the third quarter of this year. And that is a e-learning track on semiconductor and chip. Well, it's called Semiconductor and Chips Insights. So again, there's within Europe right now, there's quite a lot of looking into what types of trainings are needed to boost the semiconductor industry. E-learning modules are some of the things that we have noticed with surveys and with various analyses that are available online. So e-learning modules seem to be quite a good complement to on-site trainings, particularly for researchers in companies that may want to follow something at their own pace in order to upskill or reskill and so on. So other than the e-learning training that we are planning, we also have an expert course on metrology that we are happy to organize in collaboration. Well, it will be organized by our partners on the pilot line from the University Polytechnica of Bucharest. The exact date has not been set. However, we expect to open registrations in the fourth quarter of this year. Again, this year has been very prolific in releasing trainings to the public. As you see, not some of them have been closed, but others will follow, particularly the PDK trainings. We also intend to have new editions of those. There is the winter school that I talked about, and these expert courses. Do keep an eye out on our events page on the NanoIC project website. So there, everything related to training events, you can access it also right now with the QR code. Everything related to our training events is posted there, including details about the training, the target audience, registration links, and so on. And with this, I close my presentation